Okay, good morning, everyone. Let's see here. Let me do something here. Been having some technical difficulties. Good morning, everyone. Been having some technical difficulties this morning. Let me do something here. Been having some technical difficulties. Okay. Yeah, we've been having some problems getting into StreamYard. I think the live link isn't working, so I put that in the comments there. I think if you, let's see here, let me fix this, because and then initially I put in the wrong URL. I was missing something there. Okay, I think that even that doesn't quite seem right. Then here. Why is it I can't get this to work? Yeah, that's still not the correct URL for this. And why is it I can't see that? That should be showing up in the comments. Now, this is just one of those things that it's enough to drive one crazy about StreamYard here. See, and I need to turn off that banner there, but I don't even see that. Let's see here. Okay, let me turn off the banner. Let me turn off that live link. That's not right either. Live link is at streamyard.com/WX2NPXJ8JW. Okay, because no one joined me in the live room, and I presume because they can't get there. Normally, you're supposed to just put in live.naturalphilosophy.org, but if you do that, you're going to get this message about the conference has ended. Because I had to create my own conference this morning. We seem to be losing our administrative control over StreamYard here. So hopefully people will see that. They'll try and go to the YouTube and see that comment there so that other people can join me. That's the point of a live chat. So I see we have today Charles Lucas Jr., Mr. Lucas, and we have Stefan. And so do we have any other folks out there who are watching us on the live stream? At least we can confirm that the YouTube channel is working, so that's good. But still, no one else is here in the live room. So I guess I'll get started then with the morning's news, and until hopefully someone else shows up or you guys have got a question. So I'd like you guys who are watching. We've got 5 people watching on the YouTube. So I'd like you guys to kind of help lead the discussion this morning by asking a question. So I'm just going to ask you this question, which is that if you met some highly advanced civilization, say they were, like 1 billion years ahead of us, and they obviously knew everything there was to know about physics, what would be the one question you would want them to answer, right? So presume that, you're dealing with somebody who obviously knows what all the answers are. But what would be the one question you would ask them? So I want you to think about that and put that in the chat so we can discuss that. But to just get things started, there was a response from Draft Physics to my last response to him. So we're kind of having fun going back and forth. And unfortunately, I only got to watch like a little bit of his response there. I'll have to go back and watch the rest. But the part that I did watch, concerned this because I made an assertion and probably, when I think about it, it's like, yeah, I was probably just baiting him. I was just baiting Gary, because I said that if an actual experiment came up which disproved his theory, that he would probably not accept it. And it's like, okay. So he said that was BS, and it's like, yeah, I said, that's then good. Just like, I think that's very good when a dissident can agree on like a specific experiment, and if that doesn't come true, that he would would say that he would accept that experimental result. So in this case, the experimental result that we would be looking for is that if we say transmitted a carrier wave, this is not AM or FM encoding. It's just like, you send out a raw wave into space, and you send a square wave, for example. My hypothesis, which says that waves exist and that this is a wave phenomenon, would say that if you just had a raw receiving antenna and you just like hook that thing up to an oscilloscope to see what the waveform that is being received is, my hypothesis says is that you would in fact see a square wave, not maybe a perfect square wave, but it would follow whatever you were transmitting, versus Draft Science's hypothesis, which would say that no matter what kind of signal you put out in that transmitter, you're going to get back a sine wave, right? Because Gary's hypothesis is that even radio waves come in these clumps, which I would say is not correct. But I think that's an experiment we can all agree upon that can, tease the differences out between these two experiments. So I did some Googling on this, and you find these people who basically say things like, "Oh, you're never going to get a perfect square wave out of there because of the frequency requirements." Apparently, the very sharp rise requires like infinite frequency response to happen, or that the radio waves would act at, the space medium itself kind of acts like a low pass bandwidth filter. So once again, you can send a square wave, but you're not going to get exactly a square wave. But it's like, that's not the point. The point is whether you're going to get anything that even looks like a square wave versus something that looks like a sine wave. And there were also these other people who, in theory, they're saying things like, no one would want to broadcast a radio wave that way, since the most efficient radio wave would be a sine wave. But they're saying they would agree with me in practice that yes, you could broadcast a square carrier wave, and you would receive it in the receiver as a carrier wave, but with no actual evidence of having done that experiment. That's just sort of, based on the crowd mentality of how we believe how these things work, that's what we would expect. But that is not a physical experiment. I mean, it's like, come on, guys. It's like, so someone asked the exact question we're looking for, like, can you transmit a square carrier wave? And no one actually comes up with any actual experiments, which in practice is not that hard to do. All you'd have to do is get a function wave generator, have it generate a square wave, feed that directly into an antenna, and then right next to that receiving antenna, right next to the transmitting antenna, have a receiving antenna, and just hook that directly up to an amplifier, and you could just observe what it would look like if you attempted to transmit a square carrier wave. And it's like, yeah, okay, so I still can't find the actual experiment. I guess I still need to look further to see whether I can find that. But oh goodness, my camera seems to be glitching out on me. So I'm gonna have to see if I can try and fix it. I think the camera cord is being pinched, flaking out of me, and I can't switch computers. So now we're gonna have to like not only go without any other guests in the live room, but now we have to go without my picture. So, but maybe I can share my screen and we can go look at maybe Gary's video or something. So let's go ahead and see whether I can find that. So I'm a little frustrated that I can't find, that experiment. So, Gary might be right that the reason why I can't find that experiment is because no one's done it, which is kind of exactly, my frustration with my theories, because it's like, yeah, you have the same thing that I'm looking for a specific experiment. You'd think it'd be easy enough to do, but yet no one seems to actually do it. So let me see if I can find the email message thread here. Now, to that same point, I was also similarly challenged this week to, and I'm going to share this to support my own theory, which is that the only particles in the world are the positron and the electron, and that you will never ever find a fractional charge. Right, so that's definitely something that my theory has to deal with. So let me share my screen here. We're going to share audio. We're going to share that. Okay. So now you can watch something else since my camera isn't working here, right? So I started out by saying that, so I had a criticism of Cornelius, which said, he doesn't have anything really written down per se. So it's kind of hard to nail down his hypothesis if he doesn't really have anything written down. But you can go to my websites and you can see all of my stuff, written down. So, if you click on this theory link here, you can get all the written descriptions, and I have the basic theory written out in these paragraphs, and I have these links so you can go to my specific papers about each of these topics here. So like that would be like one paper, and there's another one about saying this is my main point, that everything is made out of positrons and electrons. The other links that I have here are also specific links to like the official papers that I have that, let's see here, 404 not found. Oh, I think that needs to be HTML. So sorry about not testing that link there. So here I have all of my official, these papers look like journal kinds of papers here, and I've posted them up on Vixera. So if you look at that, then you can see that there is just a lot of, why is that not coming up? It's like, why is like nothing working this morning? If you click on that, then hopefully the paper will show up. As my computer will ever catch up and start showing this thing. Okay, so there's an example of one of my papers where I'm arguing that gravity is just the electrostatic force. It looks very fancy, nicely formatted, and maybe a few references. And fairly short, so that's like 3 pages, right? So, and no math at all. So if you're looking for something, so you don't have any excuse not to read these because it's like, it doesn't have any math and it's only 3 pages. You can read that in 5 minutes, so no one should complain about that. But getting back to the original point here is that, he reads my stuff and he recognizes my fundamental postulate here, and that there can never be a fractional charge. But then he brings up this direct observation of a fractional charge. Okay, now, so if this is true, this totally blows away my theory, because a fractional charge can't possibly exist in my hypothesis. There's just no 2 ways about it. So, and he says, I suppose you are in denial about that. So, just like the way I challenge Gary is like, okay, well, he's challenging me, and I think that's perfectly fair. So I go in and we can click on that link and see what it's about. Now, let's see here, accept all cookies. So this is from the journal Nature, very prestigious journal. And this is from 1997. And unfortunately, the only way to actually read this article is by renting or buying it for $8.99. And I guess that's better than the $30 it costs to open up an academic journal. And just as an editorial aside, I think this is completely ridiculous, because most of this research is funded by government money. Access to this stuff should be free, or at least like $1, but I guess $8.99 is better than $30, but still access to this stuff is should be free. But so the only thing we have to go by here is the abstract here. And, they're saying that it's been well known that electrical charge is quantized in units of the charge of an electron. So, but there's this theoretical prediction by Laughlin of the existence of fractionally charged quasi-particles proposed as an explanation for the fractional quantum Hall effect. So, some guy is predicting that there's a quasi-particle, whatever the heck that is. It's a theoretical prediction and predicts the result of some other effect called the fractional quantum Hall effect. I haven't had time to figure out what that is. But in any case, it says the effect is a phenomenon observed in the conduction properties of a 2-dimensional electron gas subjected to a strong perpendicular magnetic field. Okay, this effect results from the strong interaction between electrons brought about by the magnetic field, giving rise to the aforementioned fractionally charged quasi-particles which carry the current. Here we report the direct observation of these counterintuitive entities by using measurements of quantum shot noise. Quantum shot noise results from the discreteness of the current carrying charges, and so is proportional to both the charge of the quasi-particles and the average current. Now that just seems to be a lot of assumptions piled on top of each other, right? Our measurements of quantum shot noise show unambiguously that current in a 2-dimensional electron gas in an FHQ regime is carried by fractional charges, E divided by 3 in the present case, in agreement with Laughlin's predictions. Okay, so that would definitely seem to be something which is incompatible with my primary hypothesis, right? And there would seem to be some evidence against it. So it's like, so how am I going to react to that? Am I going to react the same way that I said that every other dissident would be, which was to deny the results or dismiss the results, or and honestly, I'm going to be just like a dissident, and I'm going to dismiss the results. So but it's not an unreasonable thing to say that this is contrary to the title here, direct observation of fractional charge. This, just even based on the abstract, doesn't seem to be anything close to a direct observation of fractional charges. I mean, generally speaking, you don't measure quantized charge using a current. And things like noise tend to be, I don't know, noisy, right? So it's based upon, a bunch of things that we don't know, like, fractional quantum Hall effect. That's certainly something is probably observable. But the existence of these quasi-particles is theoretical. But really, I should probably go and look at this more carefully. Now, sometimes you can actually find these articles directly out in the open, just Googling them. So just for the heck of it, let's go ahead and directly Google that and see whether we can find it. Aha, see, it's an Arvix. And Arvix is free. So this is exactly the same paper. So we can go and bypass the paywall and get this paper directly. Okay. So, but as a good dissident, I should be able to go and look at this and see what they did. And it's not a long paper, okay? It's not a long paper. So let's go see what they're saying here. So we just read the let me see if I can make this a little bit bigger for you guys. Where are the controls for this stupid thing? Okay. Okay. We're going to make it bigger here. Now, let's see, but before I do that, I want to make sure that we don't have any other questions going on. Let's see here. Oh, we have some other people here. We have Harry here. So welcome, Harry. I'm glad to see that you were able to find us. But we do have some comments here. So we have, dissident is a euphemism. Most YouTube dissidents are rightly scorned and ignored by mainstream because they barely understand 5th grade math and physics. I'm not exactly sure that's true. I mean, dissidents tend to believe in a lot of things which are different, but I don't think they, generally speaking, misunderstand 5th grade math. And I think, a lot of times that saying that they barely understand physics is simply because they are not using current physics, but I think that's probably the case. So, not defending mainstream, but most dissidents are a joke. And, but, that may in fact be true. But my philosophy is like 95% of everything is trash. But the only way to get to the 5% of the good stuff is to wade through the 95% of the other stuff, right? And there's no way you can avoid wading through the other 95% of the stuff, which is just trash. So, and because of that, we can't really ignore or throw away or somehow judge the rest of the stuff, which is trash. But there is a chance that, one of us is potentially right. I wonder if my camera is working. Let's see, is my camera working? Oh, goody, my camera. No, my camera is continuing to not work. Okay, so getting back to, let's just take a look at this paper then. Now that we've actually been able to find it, and it's not a very long paper. So he's saying the energy spectrum of a two-dimensional electron gas subjected to strong protective magnetic field consists of highly degenerate Landau levels with a degeneracy per unit area of blah, 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 blah. A lot of Greek. Similar phenomenon occurs with fractional filling factors. It is known as a fractional quantum Hall effect. In contrast, the IQH effect cannot be explained as subterranean and believed result of interaction between electrons brought about the strong magnetic field. Laughlin argued that the FQH effect can be explained in terms of quasi-particles of fractional charge. Q equals E divided by Q, although his theory is consistent with a considerable amount of the experimental data. No experiment directly showing the existence of the fractional charges exists. An early experiment were proved to be in principle inadequate to reveal the fractional charge. A more recent experiment based on resonant tunneling, the difficulties in such experiments provide only the average charge per state, not the charge of individual particles. Quantum shot noise, on the other hand, probes the temporal behavior of the current and thus offers a way to measure the charge. Indeed, as early as 1987, suggested that quasi-particle charge could be, in principle, be determined by measuring quantum shot noise in that regimen. However, no theory was available until when recognized that the transport, blah, 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 making use of liquid model. Based on this model, so predicted that quantum shot noise generated due to weak backscattering current at zero temperature should be proportional to the quasi-particles charge Q and the backscattered current IB. So somewhere in there is the key here. So they're using a liquid model predicting quantum shot noise, fractional filling factors, and at zero temperature. Of course, zero temperature is like impossible to obtain. So I'm not quite sure I see that. So they have a picture of a diagram here. And they have a current noise, and that seems to be a straight line, whatever the heck that is. So somewhere around there, they have to come up with a 1/3. So current fluctuations outside the cryostat, the amplified signal is fed into blah, blah. So this is basically how it's done. This allows translation of the spectrum analyzer output into spectral density of the current fluctuations. It still introduces fluctuations in the circuit. The unwanted current noise must be subtracted from total measured noise in order to extract the shot noise associated solely with QPC. You do both the electron temperature and the contribution of our amplifier to total noise. Note that the temperature, 57 microkelvin, is very close to that of the sample holder. We got a whole bunch of Greek here. We have a graph of quantum shot noise. And you can just tell a difficulty of when you pick up a journal article, you know, just trying to understand what they're doing. So that's why I know I'm going through this. You know, if you guys think this is painful and boring, well, let me know in the comments. But I'm just trying to figure out, going through the process of trying to figure out whether what they're doing here is actually valid, right? So we know how they measure it. We have a little idea of what the theory is. Now, the rest of this, the magnetic field was swept from 0 to 14 Tesla. So this is telling you basically, you know, how they did it. and they get excessive noise. Noise is measured upon partially reflecting the current is drastically suppressed compared to the noise, compared to the absence of the magnetic field. But so far, I haven't seen anything about the actual fractional charge. Now we have another graph here showing quantum shot noise as a function of the backscattered current. So what do we have here? On the bottom, we have current, and in the vertical axis, we have the noise. And we can just simply see that as you increase the current, the noise increases. So I'm guessing that this graph, let's see here, what's the green graph? Quantum shot noise is a function of the backscattered current Ig in the fractional quantum Hall regime at V equals 1/3 for two different transmission coefficients through the quantum point contact. Open circles and squares. The solid line corresponds to equation 2 with the charge, the solid lines with Q equals E divided 3 and the appropriate T. For comparison, the expected behavior of the noise for Q equals E and T equals 82 is shown by the dotted line. Okay, so here's the key, is that they're saying that if fractional charges exist, then they should be getting results like the blue and the red line. If fractional charges do not exist, then they would be getting the equivalent of the green dotted line. So, and I presume that the little squares and the dots are the actual experimentals results in there. So they're saying that they've seen the fractional charges rather than the main charge based on the increase in noise versus the current. So I think that is the basics. As our data fit very well the expected noise of a current carried by quasi-particles of charge Q divided by 3. The backscattered current is calculated using the transmission T deduced from the ratio of the conductance to blah, blah, blah. The slope of the noise versus backscattered current curve increases with the applied voltage approaching the expected slope, and voltage is larger than as expected. For comparison, the expected noise for Q equals E, and the same G is also shown, which is what they did there. So we have another graph here. Quantum shot noise as a function of backscattered current for V equals 1/3 for 3 different temperatures and constant transmission coefficients through QPC. So the only difference here is the temperature versus the backscattered current. I wonder why they did that. The noise tends to saturate at even larger backscattered currents. Note the deviation of the data points from the solid line. The additional noise suppression is accompanied by an onset of nonlinearity in the IV characteristics. The nonlinearity in the FQH regime may result from the interaction among the electrons and the energy dependence of the bare transmission coefficients and from the finite excitation gap. These 3 sources are practically indistinguishable. Nonlinearity complicates the otherwise straightforward interpretation of our results, and we thus choose to show data in a smaller voltage range and for moderate reflection coefficients where I-V is linear. In order to further investigate the behavior of quantum shot noise at the FQH regime, we measured the noise versus backscattered current for 3 different temperatures and a fixed transmission through the QPC. The data fit the curves expected from equation with Q equals 3. Note that equation 2 with charge Q equals 3 to suggest not only that the amplitude of the noise is proportional to Q, but also that shot noise is observed above the thermal noise at a characteristic voltage 3-fold larger than the value for non-interacting electrons, because the potential energy of the quasi-particles is V divided by 3. The agreement between data and the detailed shape of equation 2 at small backscattered currents gives us an additional indication for the existence of a smaller charge, E divided by 3. In conclusion, our noise measurements unambiguously show that the current in the FQH regime at filling factor 1/3 is carried by quasi-particles with the charge E divided by 3, in contrast to conductance measurements that measure the average charge over quantum states or over time. Our quantum shot noise measurement is sensitive to the charge itself. The magic of an apparent smaller charge due to the electron-electron interaction is a beautiful manifestation of the strength of the theoretical methods used to predict such a counterintuitive behavior. During the writing of this manuscript, we became aware of similar work in which the authors measure same charge at a filling factor V equals 2/3, also using shot noise measurements. So, and that would be reference 14. So these guys, and this work was partially supported by a grant from the Israeli Science Foundation, a grant from the Austrian Ministry of Science, Research, and Art. Once again, research supported by government taxpayers and should be free, not $8.99, but we managed to find it anyways. So I guess the importance here is the relevance of this equation here. So this equation is representing all of these theoretical curves, and they're claiming that there's a fit here. So I'm not even quite sure what all these things are. We have two KBs, there's got QBs. So are they setting like the Q to equal to like 1 in this and then making some prediction here? So unfortunately, there's just no way in heck I'm going to be able to understand what that equation says, or judge as to whether it is a valid thing for you to be doing. But ultimately here, what we have is an experiment which predicts this noise level based upon some theoretical considerations with this equation to produce the data here. So the question is, as a dissident who cannot accept this result, what is going to be my reaction? Well, of course, my first reaction was to go and actually read the article and see if I could figure out what they were doing. And then my second reaction is that once I figure out what they're doing, to lodge criticisms as to why this is not valid. And so I would say my criticism is that you're measuring noise here. You're not actually measuring the charge. What you're doing is that you are making a theoretical prediction, and it's like, so you find some data that does, agree with those predictions, but it is all kind of based upon all the previous examples that you say about, this suggestion that the quasi-particles are there and that there is some level of noise which is greater than, the only differences between the predicted one is basically the slope, and they're basically expecting more noise to appear. Now, I'm not 100% sure about how this blue line actually, matches up with this equation. The standard trick is that you get your data and then you futz with the equation so that your line falls on the data, which is sometimes a valid thing to do. But in the end, the squares and the circles are the only things you're actually measuring. And this doesn't seem like particularly interesting data. It seems kind of linear, pretty much. And except for these little bits at the end, they've got these other little charts here. So their data is clearly off. in the higher range, the backscattered current, I think maybe they were saying something about that didn't seem terribly accurate. But the question is whether this is legitimate, whether you can say that this experiment should have produced that. Because what they're clearly not doing is actually measuring an individual charge from an individual particle. We're measuring an overall characteristic from a very large number of particles based on a theory which might be questionable. So I can see that there's definitely a large possibility for this being incorrect. But the other point that I was trying to make is that other people have to corroborate this. So it's interesting to say that there's this other reference here potentially corroborating this idea that there are fractional charges. So we can probably do the same trick and we'll see if we can look that up. And the internet is a wonderful thing. I mean, just like 30 years ago, no one would be able to do this. It would just be too incredibly difficult to just look up all of the stuff. But here now in 2020, all of this stuff is at our fingertips here. So we've got that. So that's the original article that we saw. So here's another, a shot in the arm for fractional charge. So maybe this is the theory of fractional quantum Hall effects applies the existence of quasi-particles, collective electron states that have fractional charge. New experiments provide a direct measurement of these charge of these strange states. So one of the most basic features of the physical world is a quantization of charge in units of electron charge. The only exceptions are quarks, which have charges that are multiples of e divided by 3, but they are inseparably confined inside nuclear particles. Yes, how convenient. Otherwise, all observed charges in nature are integer multiples of e, so it's quite surprised when Robert Laughlin in 1982 theory of the fractional quantum Hall effect made the bold proposal that objects with fractional charge could exist inside tiny semiconductor devices. In the past 15 years, nearly every aspect of Laughlin's theory has been experimentally confirmed, but a direct observation of the fractional charges of the Laughlin quantum particles has remained elusive. Now, two groups have performed a new class of experiments which probe shot noise in the quantum Hall effect and provide compelling evidence for the fractional charge. Imagine if you were in a house with a tin roof during a hailstorm. By listening, you could determine the size of the hailstone. Small stones would generate pitter-patter, almost indistinguishable from continuous noise, whereas larger stones result in less frequent yet louder crashes. Clearly, the temporal fluctuations in the sound depend on the size. This is the essence of Shakti's 1918 shot noise theory for the fluctuations in the current flowing through an electrical circuit. Provided the particles flow independently with an uncorrelated Poisson distribution, their charge is equal to the ratio of the mean square fluctuation in current to the average current. So their charge is equal to the ratio of the mean square fluctuation in current to the average current. So by carefully measuring current fluctuations, the Picatto et al. And Semir were able to determine the charge of the objects carrying current in their experiments. They were not electrons, but particles with fractional charge very close to e divided by 3. The experiments were performed on a two-dimensional gas of electrons, which is confined at the interface between two semiconductors. When cooled to a few degrees Kelvin and placed in a magnetic field of several Tesla, such a system shows the integer quantum Hall effect discovered in 1980 by von Klinsing, in which the Hall conductance GH is quantized in integer multiples of the multiple fundamental unit. This is a quantum mechanical extension of the classical Hall effect in which a current-carrying conductor in a magnetic field develops a voltage perpendicular to both field and current. Okay, 2 years later, even in stronger magnetic field, Stormer and Gossard observed quantization with a fractional value, G equals 9/3, and other fractional values have been observed since then. This new behavior of fractional quantum Hall effect could not be explained within the conventional theory of metals. However, shortly after its discovery, Laughlin proposed that electrons in such strong fields form an exotic new collective state which bears some resemblance to the collective state that occurs in superfluid helium. The central feature in Laughlin's theory is the existence of quasi-particle excitations with fractional charge E divided by 3. Although they are built out of the collective motion of many electrons, these quasi-particles are spatially localized lumps of fractional charge, moving inside the two-dimensional electron gas. They behave in much the same way as ordinary particles do. Of course, the quasi-particles can only exist inside the electron gas, unlike electrons, which can be added or removed from it. Observation of quasi-particles charge is difficult because at low temperatures they tend to be pinned in space by impurities. However, quasi-particles are liberated at the edges of this two-dimensional sample. They are free to flow in a single direction determined by the magnetic field along a narrow, effectively one-dimensional channel. The experimental challenge is to measure the charge of the particles forming this exotic one-dimensional fluid. Okay, so they route all these particles through a gap, making it basically a one-dimensional flow. And somehow we see charges flowing that are only 1/3. So I like this article much better because obviously it's more meant to design for human beings to actually read. So less math and more explanations. An earlier approach to measuring this charge was to make a small island in the two-dimensional electron gas, an area depleted in electrons. Number of quasi-particles in the one-dimensional channel encircling this anti-dot can be varied by changing either the magnetic field or the voltage on a nearby metallic electrode. By measuring the changes necessary to bind each additional quasi-particle, the fractional charge can be determined, provided one makes several plausible assumptions about the area and capacitance of the anti-dot, as well as the effects of quantum interference. Although indirect, this procedure was successfully implemented several years ago by Goldman and Su. The idea of using shot noise to measure fractional charge dates back to Stormer and Su in the mid-1980s. This is an appealing idea because shot noise is a classical effect, which is simpler to interpret. In 1994, we suggested that a quantum point contact formed by pinching together the edges of an electron gas would be an ideal geometry for such an experiment. There, Sakti's assumption of uncorrelated motion satisfied, provided the charge carriers flow through the pinch-off point at a very low rate by quantum tunneling. This occurs in two geometrical regimes. If it is strongly pinched off, the sample is effectively split into two, so the weak tunneling current must be carried by electrons, and shot noise with charge E is expected. However, in the opposite extreme of weak pinch off, the quasi-particles can tunnel from the top and bottom edge through the quantum Hall fluid, providing the rate for this is small. The resulting shot noise should be exactly E divided by 3 times the averaging tunneling current. They're saying that the shot noise should be E divided by 3. I mean, that's not measured. You're telling me that it's going to be that, even though you're using particles, well, quasi-particles. Both of the new experiments measured the fluctuations of a small current flowing through such a contact point constructed using state-of-the-art lithographic techniques. Elaborate filtering minimized the noise of the external circuitry, allowing the intrinsic fluctuations generated by the point contact to be isolated. The charge of the quasi-particle was determined from the measured shot noise in the limit of a weak pinch-off. The final results were unambiguous. The quasi-particles have fractional charges. Fractional charge is no longer solely in the domain of elementary particle physics. So I suppose I could live with the result, which is that a quasi-particle has a fractional charge. Now, I suppose the question is, what in the heck is a quasi-particle? Because this is saying that the quasi-particles have the fractional charge, but yet the electron that these things are based on would still have a full quantized charge. So they're saying these and as near as I can tell, a quasi-particle based on this article is something like some collection of charges which move in a geometric fashion as if they were a particle, but are really just like a group of particles. So it's something like, you have like some group of electrons, like 4 or 5 of them, but due to their shape, they carry something other than what you would expect as the full complement of charges for whatever that distribution is. And so maybe it's the quasi-particle is like some electron which you can only observe at a quantum distance of like 3 units away, where its field strength is like 1/3 of what it normally is. And if that is the case, then I would say this really doesn't say anything about, say, the charge of, say, electrons. The charge of electrons would still be full electron charges. But if you build these, whatever these quasi-particles are, then you can observe them to have less by their field strength, I suppose. And that's all they're measuring here. Now, I like in the article here, at least they give a sensible analogy to what they're measuring, which is that you have very large and infrequent hailstones compared to smaller hailstones hitting your roof. So that's definitely something which you can actually wrap your head around versus some gigantically long and confusing equation, right? Now, I'm still not 100% understanding what this stuff is, but I think it's an interesting exercise to try and pursue these questions the way I think dissidents ought to pursue these questions, which is to not ignore contradictory evidence to your theory, but to, in fact, be a scientist, pursue the references to the extent you can. And I just showed you how you do that, right? You get the original article, you hit the paywall, you go search for it, you find it in Arvix, and then you can read it for free. Then you can go and read that article and find any other additional references, and you can find that for free, right? So, and you can do it all within the short span of an hour, which is what we just did. So let's go back and let me see whether we have any comments about here. Let's see here. The only other participant we have today is Harry Ricker. So Harry, do you have any comments about fractional charges? You'll have to take yourself off of mute if you do. If not, let's see here. Let's see what we have. We have some comments in here. It says Ham asks, how do you define electron and positron? Is it from the standard model? If so, you're assuming the rest. Okay, so how do I define electron and positron? Yes, I accept the standard model definition, the mainstream acceptance of the positron electrons, not anything different from that. So if so, you're assuming the rest. So I'm wondering what's the rest? And what am I assuming? So maybe that means that everything that I've built out of the positron and electron is assuming the rest. In which case I would say, I wouldn't say it's so much an assumption, but a hypothesis. So for example, if I say everything is made out of positrons and electrons, and things like protons and neutrons and all of this particle zoo that we've observed, there's like, at least, 30 or 50 particles. They all last like a microsecond or something like that. But every one of those has to be built out of positrons and electrons. So if I say that a proton is built out of 2 positrons and 1 electrons, is that an assumption, or that's my hypothesis, or that is like the testable hypothesis, I suppose, or maybe that's what you mean by I'm assuming the rest. The hypothesis is that everything that you observe is made out of positrons and electrons. And let's see here. Saying don't be shy. We've got a reference here in Facebook. I don't know what that is about exactly. Let's see here. I'm not sure I can actually copy that out so we can see what that goes to. I wonder if I can see that. Because I have a problem. There's no way I'm going to be able to copy all those links there to see what that's about. But let's see here. So, Bill Lucas. So Bill has joined us in the live stream. So, and I'll let you go ahead and explain your comment here. Let's see here. I don't think Bill is moving here. Are you there, Bill?
I'm here.
Oh, good. I'm getting tired of hearing myself. So we've got this comment here.
Divided by 3? I mean, that's not measured. You're telling me that it's going to be that, even though you're...
Oh, no, it was done
particles, quasi-particles.
60 years ago.
Both of the new experiments measured the fluctuations of a small...
I'm getting a very strong echo here.
Constructed using digital art lithographic techniques. Elaborate filtering minimized the noise of the external circuitry, allowing the intrinsic fluctuations.
Yeah, we're like totally...
The charge of the quasi-particle was determined from the measured shot noise in the limit.
Bill, you're going to have to mute your
quasi-particles have fractional charges. Fractional charge is no longer solely...
All we hear is me reciting the paper.
So I suppose, I could live with the...
So that's weird. That's like, just like you're playing me back like a minute ago. But your comment here is that the structure of the neutron proton in terms of quarks with charge E divided by 3 and 2E by 3 by scattering experiments has been formed since the 1960s. Although I would argue that if that were true, then the mainstream would point to that as a direct measurement of fractional charges. Now, I've seen the arguments that you have there, but if the mainstream itself doesn't agree that those are direct measurements of quark charges, then I'm not quite sure how you can exactly claim that either. Because I've looked at these things and you can definitely see some things. I mean, there's a suggestion in scattering experiments that there are 3 things in, say, the proton, although I have my doubts about that because it's all based on they're trying to determine, they probe the proton to see where its charge density distribution is, and you can see that it has some positive parts and there's a negative part and there's a positive part, and therefore since it varies, like it has these 3 little sections to it, we say that that's evidence of there being 3 things that make up the proton. So now I find that a little bit not believable, but the fact that there are 3 things doesn't mean that those 3 things are fractionally charged. It's just about a ratio. Like if you fire an electron at something, I would think that you would be able, if that thing is made out of multiple charges, I'd say it's possible to determine what the ratio of those charges is. But I don't think that you could ever really determine what the magnitude of those charges are. So it's like the charges could be like 5 times the electron charges, but if they are all like evenly distributed, then all you're going to be able to do is detect the ratio, which is that there's 2 positive charges for every negative charge. I would think that's the only thing that you would be hypothetically be able to detect, just the ratio. So I guess that's kind of my response to that it's still not very convincing. You know, we've not been able to isolate a quark. So if someone actually comes up with the experiment and says, aha, there's the quark, there's the up quark, there's its 1/3 charge, and we measured that, right? We put it through the cloud chamber, and it only bent 1/3 of the way compared to the actual electron that was right next to it. Then, you know, that would be clear, unambiguous evidence that fractional charges exist and that quarks exist. But we've not seen actually any of that. So you can, and there's actually no physical reason why we shouldn't be able to see that. There's no actual theoretical reason why we shouldn't be able to observe separate quark charges. And definitely there have been experiments that have tried to do that, and they've all failed miserably. So I'm arguing that, you know, there's been so much effort to find the individual quark charge and the individual fractional charges that all of that negative evidence just basically has to point to the other alternate hypothesis. All of those experiments actually point to support the hypothesis that quarks do not exist, and that the only thing that actually exists are just the positron and electron charges. You know, the math works out. I'm not sure why people like the 1/3 charges so much. So let's see if we have any other comments here today. Nope. So I'm still looking for questions from the audience. So today we were talking about whether fractional charges can exist. So we have some, we just reviewed 2 articles that indicated that, you know, such fractional charges might exist. And it looks like these fractional charges exist in things called quasi-particles. So to an extent, they're not actual particles, but probably some conglomeration, some geometric arrangement of whole charges, but somehow these allow fractional amounts of current to flow, as measured by this quantum shot noise, which is several layers separated from an actual measurement of a fractional charge on an actual particle versus a quasi-particle. But I think that was an interesting exercise to go through and try and pursue that. So Bill Lucas also comments, one must be able to explain the existence of the observed elementary particles. So that's absolutely true. And of course, my hypothesis would say that everything must be made out of positrons and electrons. So every single elementary particle you have ever observed has to fit that hypothesis. And, you know, to the extent that it is possible, I think I've done that. You know, to the point where, you know, someone said, you know, because this is what they always say, it's like they can't be made of positrons and electrons, you know, because you can't explain, like, you know, the super heavy charm quark blah blah super something particle. You know, and I took on that challenge. I took like the heaviest elementary particle that we know of, and I deconstructed its decay chain, and in fact, it can be explained in terms of only positrons and electrons, and that's easy because when it decays, that's what it falls apart into, right? You know, you have this super heavy particle, which is still theoretically made out of, say, 3 quarks, but it falls into like 27 different pieces. You go from something that was like made out of 3 things to 27 pieces. But I'm saying that the only reason why it fell into 27 pieces is because it was 27 pieces to start with, and here are the pieces. And you can just follow the decay chain all the way down and say exactly how many positrons and electrons that thing was made out of, and you can always do that. Any observed elementary particle that decays, you can positively explain it in only terms of positrons and electrons, simply because that's what they all decay into. You know, they can only decay into either the stable particles of a proton or an electron, or it decays into some other unstable particle like a muon and that sort of thing. And all of those things eventually decay into nothing more than positrons or electrons or energy events like photons. So I would say that. So Alistair has another comment. Says, if it reduces to 2, there has to be the ability to build upwards from the result. And yeah, I would totally say that is absolutely true. I mean, that's kind of the hope of science, that you try and start, that you'll get something simpler. We have Alistair here, so I've added you, Alistair, to the talk here, so you can comment yourself about what you were saying here, which is that, let's see, where are the comments here?
I was saying that if it reduces down to a positron and an electron, then from just positron and electrons, you have to be able to show that you can build something, you can build back upwards. So like when you reduce 50 by 5 and you get 10, you've now got 10. How do you get back to 50? Well, you got to multiply by 5. So you know that 10 and 5 produce 50. But you've divided down to where you got a positron and electron. All right, so now with a positron and electron, how do you get back to everything you came from? It should be reverse the calculations. Well, then if you can reverse those calculations, you've got the proof that the electron and positron can produce everything.
Yeah, well, most of that is done for us, because in any of the listings of the elementary particles, they all include the decay chains. So you can follow every single step that a particle goes through before it eventually ends up being positrons, electrons, or other stable particles. Like,
well, you say the particles reduce down to being an electron and positron, but the particles that we envision are swimming within a something. So then what's that something? Or is it nothing?
My hypothesis is that something is, in fact, also a sea of positrons and electrons.
Okay, so then you've changed the situation. You're not now looking at the particles that reduce down to what you found. You're saying, I'm building back up, and then I'm going to add into everything else the same thing. But now you're changing the situation. So you're no longer just working towards what you reduced from. You're building back up towards what you reduced from, and then adding a whole bunch and thinking it's going to be the same result, but you got to accommodate for the fact that you just added a whole whack, don't you?
You mean just filling space with positrons, electrons?
Then you have to be able to say, why does it have this impact on what I just proved I could build back up? Or why does it have no impact on what I just proved I could build back up? Otherwise, you've built back up to something that's incomplete.
Well, I mean, it seems very simple. Like, for example, I would take a positron, well, 2 positrons, electron, I glue them together, that's the proton. Now, the fact that that structure is surrounded by all these other dipole positron electron particles really has no relevance, right? It's like that's outside of the proton. So I just don't see how that would possibly have any effect. And then if I say, if you take two protons and you stick those two together, then you get, helium, okay? And, and that is surrounded by the positron electron state. So I think we have Bill raising his hand. So Bill, go ahead and see if you can unmute yourself and see whether we can hear you.
I'm unmuted now. Can you hear me?
Yes, we hear you now. We hear you clearly. Go ahead.
Okay. We are able to measure the mass of elementary particles now to 8 significant figures. If we take an elementary particle and say, what is its rest mass when it's not moving with respect to the environment, then if it's made of electrons and positrons, the total mass should be the sum of the electrons and positrons.
Why?
But it doesn't work out because the numbers are not even to 5 significant figures, but we can measure it to 8. So we see that there's something wrong with that. And also we can see when we change, when a heavier particle decays and we look at all the decay products and we sum the energy that's released, and we don't end up with any electrons coming out. It is difficult to explain what's going on. And the approach that I've been promoting with solitons which have a charge of E/3. It is able to explain these things. So, for instance, we're able to predict the mass of the 96 experimentally measured masses of elementary particles. The rest of the elementary particles are projected by various theories, but have not been observed directly. But of the ones we can observe directly, we have 96. You need to be able to explain to 8 significant figures the rest mass of each of these particles and explain how they decay and account for all the energy that's in the decay particles and the original particle. So the standard model with over 400 elementary particles, 300 which have never been observed directly. The other particles were invented so that the standard model can predict most of the masses and properties of the 96 observed elementary particles, but they still can't predict the mass of the electron and its properties. So, but the soliton model can predict it. And by predict it, I mean that from just pure theory, you can predict what you would measure experimentally for the masses and the charge and all that kind of stuff of all the different experimentally observed elementary particles. So that's what you need to do, is be able to explain the properties, the decay modes, and the reactions. If I take 2 electrons and I bang them into each other, I get a bunch of things out. You've got to be able to explain what that is. And some of the particles that come out are heavier than the electron, of course, and some are lighter than the electron, such as neutrinos and other types of particles. So, if you apply logic tells you your model doesn't work if you don't be able to predict these things.
Okay, good points there, Bill. So I'm going to respond to that. And I'm going to ask you first a question, which is, why do you think you should be able to add the masses of elementary particles together to get their sum? So if I add something that contains like 3 electrons and a proton, why do you say it would have to be 4?
Well, it's not 4 because the proton is heavier than the
I'm
electron.
just saying theoretically, you're saying that we would expect that if we think that we should be able to add together the masses of the individual components to get the total.
Mhm. So if we want to do that, let's say we take a proton and an electron, and we look at a third particle, the neutron. So what is the mass of the neutron compared to the proton? Is it slightly larger than the proton because it has the electron in it? And the answer is yes, but you also need to know what is mass. Mass, if you have like in the work that I've done, there's only one fundamental force, the electromagnetic force. There's no strong interaction, no weak interaction, no gravitational force. So all mass is something that can be defined entirely in terms of electrodynamics. And so that is why we're able to predict the mass of 96 observed elementary particles. And we're also able to predict their decay modes and the amount of energy each particle will have when it comes out of that decay. And so those are tasks that are that need to be done. The standard model can't do it. You can do it partially, but they have invented hundreds of other elementary particles which we have never observed, and we have no way of observing, to try and see if they can predict what we do observe. And so that's difficult. And we're watching the presidential elections right now, and we see the politics and the kind of arguments that they make against one another and their ideas. You have the same kind of politics in science. And when you successfully do something that the people who are leading in the politics don't like, they'll do things like get you fired from your job, just to get rid of you, get you out of the scientific community.
Yes, but fortunately here in the CNPS, you can say whatever you want and you won't get fired, right?
No, but you haven't.
We're not going to take away your salary.
You haven't succeeded. Your work is not better than the standard model. The standard model is predicting more things than you are. And so you have to go further. You have to explain what is the force of gravity, what is the standard force, what is the weak interaction force, what is the electromagnetic force, in terms of your electrons and positrons. So those things you haven't succeeded in doing. You need to.
Well, no. I mean, I'm surprised you would say that, because certainly those are all things that, at least my hypothesis, my own personal hypothesis, definitely covers every one of those, right? I definitely cover the nature of the electromagnetic field. I definitely cover the nature of gravity itself. The only thing that my theory doesn't really cover, that your theory could potentially cover, is what is the actual nature of the electron itself, right? I still haven't found any convincing.
I predict experimentally measured information. You're not predicting that. In other words,
well, you gotta be kind of suspicious when anyone says that, because anyone can what's called post prediction, which is that you know what the answer is, so you can always change your theory to match that exactly. So,
but you see, you've got 96 elementary particles you got to explain.
And you could have, carefully crafted your theory to match the experimental data. Now, I don't know whether you did or not, but it'd be actually more convincing if you could predict.
The electromagnetic force has chiral symmetry. Chiral symmetry controls the way that solitons can combine to form an elementary particle.
That
So-
is if it happens, right?
So what you do is you say, well, how many structures can I predict would exist if you are using solitons and you make try to make all your 96 elementary particles. So what is the difference in terms of the internal structure and geometry? It has to have chiral symmetry. I can't just put together particles arbitrarily. And so that is what I was able to do. And so predicting all of the elementary particles that could be measured with our accelerators so far, you see that they consist of chiral symmetries of solitons.
But ultimately, Bill, in order for this to be convincing to anybody, you would have to design an experiment which directly detects that soliton. I mean, this gets down to this whole thing that we're talking about, fractional
That
charge.
was already done. People receive Nobel Prizes for it. What are you talking about?
That's what I'm asking you. It's like, okay, so where is that Nobel Prize winning article that detects your soliton? I've never
Arthur
seen
Compton
that.
published them, and his last graduate student, Winston Bostick, published them. They were in the major physics and science.
No, I've read those, and they showed, the plasma, their soliton in the plasma, but that was clearly not the soliton that makes up the electron, right? Your plasma solitons are made of giant collections of billions of electrons in their experimental apparatus. Now, just claiming that you've seen a soliton, I mean, you can make a soliton, like with a plate in the pool. That's, but that does not in any way prove that an electron is made out of those things. That you
The
need an experiment.
soliton model of the electron has 3 solitons, E/3 charge.
And you need to show that. Where is the experiment that proves that with electrons, right? Not some other unrelated thing.
They did that. They made solitons, and then they combined the solitons to make an electron. And not only that, you can predict all the properties of the electron. In other words, you can predict its spin. You can predict its magnetic moment. You can predict its mass. You can predict.
Well, once again, I've gone and looked at what your references are with Winston Bostick and those guys, and definitely none of them say they actually found that soliton. I can almost say that for a fact. I can look at every one of your references. I can see the experiments. I can see what they did. None of that. I mean, they didn't even say they found those things. They just found that, they found these kinds of, smoke ring kind of phenomena, which is like, great. It's like, yeah, we know smoke rings exist. There's no problem with that. But to say that there is a soliton that has a 1/3 fractional charge in it, I just didn't see anything actually saying that. So.
Well, I visited Winston Bostick at New Jersey Institute of Technology while he was still living, and he was very strongly promoting those ideas, and he claimed that he had done the experiments himself. And he did a lot of experiments measuring the strength of the soliton, and the strength of the soliton is greater than any known elementary particle. And you can make a point, like a needle point, and put a soliton on the end near the end of the meter. I don't know if you can see this or not. Anyway, you can make it say near the end of the needle. Then you can stick that in a nuclear reactor. And if you can hold the needle up high enough so that it doesn't melt in the reactor, then the soliton will stay there and will not be destroyed or modified by all the particles that are going back and forth in the reactor. And
Yeah. So, Bill, if you're talking about something that, I mean, how do you think that that is, even physically possible? If you have a soliton, it makes up the electron. It's like the third of the size of an electron. How are you going to stick that on anything? I mean, that's just impossible. You can't stick a soliton
the soliton can be made different sizes.
On any probe.
The
Can't do it.
soliton can be many sizes. The electron is a particular size of the soliton that is in terms of the energy and the fields. When you have three of them together, it's a particular size. And so you can, the soliton model enables you to predict the size of every elementary particle. And you
but my thing is that I have grave doubts about the experiment that you just related as being just kind of physically impossible, right? You would not be able to, I mean, we just lack the ability to observe anything that's like, sub-electron sized, just by definition.
Well, these are not smaller than the electron.
Not observe something that small.
The three solitons are in order to have chiral symmetry, they have to be the same diameter and the same radius and cross section, and they have to be the three layers. And so there's one that's a little bit larger than the others, and the other two are a little bit smaller, and the three go together that way. But I don't know if you realize all the things that were done at MIT. They took and made a soliton, and with one soliton in each jet engine, they made a jet plane that would fly using the.
Yeah, we've heard about this. We've heard about these things, but unfortunately, we can't have any corroboration. I mean, I can't search for this on the internet and find it.
It was a public demonstration. The military was invited. The airlines are invited.
But apparently completely suppressed because, obviously, if that were true, we'd be using it. But since we don't, it must be the conspiracy of the oil companies to prevent distribution of this.
I read those articles. I may have them in my library. I'll take a look and see.
Well, once again, if you can send an actual article, I would be very interested in it. But I'm pretty sure that such a thing never happened. I'm just kind of skeptical. I mean, as a skeptic, I'm entitled to say that I don't believe you, and I don't believe you. So I don't believe they ever made it anything made out of soliton.
MIT did the publications.
And even if they did make an engine out of soliton,
they modified an old jet plane, and they flew it around the world, and they were able to fly the jet plane at a higher speed than any other jet plane has ever flown using this.
Yeah, higher than this SR-72, which we know exists.
Yeah, they're able to go at 2,000 miles per hour.
And you know that if they were, then if they were in an old jet plane, it would have melted.
No, they had to fly high enough when they go fast. And
it would have melted like the Apollo space capsule would have melted at such speed. It's just, that's what happens when you go that fast through the atmosphere. Certainly at any velocity conceivable, any old jet plane, not designed, not made out of tank. I mean, it's tough enough with an SR-72. You are out there in the edge of space. You have to be in a space suit, basically. And, the temperatures are still like, re-entry hot. Even with the SR-72, it's a very difficult engineering challenge. So when you tell me that they took like a regular old fighter, like an F-16 or whatever, stuck this soliton engine in it and went faster than an SR-71, I have to say that I don't believe you.
It was all observed by our military. They used their equipment to measure every characteristic of the plane.
Well, once again, if you have something that I can actually look up in the internet, then I would be more inclined to believe you. But
Well,
just me just knowing the laws of physics and how planes work and the claims you just made, all of that is telling me that that's impossible.
I didn't make those claims.
That's not possible.
Winston Bostick and the people at MIT who did the work made the claim.
Well, once again, if you have references, then you can support it. And I would say, great, I'd love to hear about stuff like that. But what you're telling me in my own mind, you know, given the logic of how planes work and what would happen if you were actually at such speeds and altitudes, tells me that, you know, and that's why I don't, you know, I'm not making any, you know, characterization on you. It's just that that everything that I know about physics and planes is telling me that that can't happen. So, and
Anyway,
you can understand my skepticism there, right? It's like,
I wasn't there, so I can't say I was there to observe it. But
so I think that if you're going to believe stuff like that, then, you know, you should back it up, right? You can say, Franklin, here is the article. I'm going to send it to you, and you can go look it up. And NASA says, yeah, we did that, and but we still insist on blasting our payloads using, you know, multi-million-dollar rockets that we have to hire from Elon Musk.
Hundreds of people present to observe this. Hundreds, from the military, from airlines, from the
But once again, the only source of information that I have for that is would be you. So,
well, I didn't get it.
You may have been mistaken.
Because I wasn't present and I learned about it. I did talk to Winston Bostick about that, and we had some conversations about that when I visited him at New Jersey Institute of Technology. And but I only had a few hours with him to visit. But
I think just getting back to the point, I mean, the only reason why we're talking about this is to discuss the possibility whether fractional charges exist. And certainly with the Bergman ring model, like, you know, which is what you kind of advocate for, quite clearly such fractional charges must exist. And, you know, one of the objections is that, you know, the mass doesn't add up. So if I say that a proton is made out of 2 positrons and electron, the intuitive answer is that the mass of the proton should be 3 times the mass of the electron, which it clearly is not. It's like 1,920 times more massive than what you would think, you know, 2 positrons and electron would be, right?
Well,
now the question there is, what causes mass, right?
Yeah, I'm able to predict both the inertial mass and the gravitational mass for all particles. Now,
and once again, it's like you're predicting.
How do you make a distinction in your work between inertial mass and gravitational mass?
See, as a skeptic, I would say, well, you can always do that. I mean, I could do that, just given sufficient amounts of theoretical psychobabble. I can take the existing values and say they exactly match mine, right?
It's I also predict big G, gravitational constant.
And for me, the thing about gravitational constant is you have to predict that it's not a constant because it's not. So
it's decaying, but we know what the
and it doesn't not necessarily decay, but it's like we can measure it in different ways in the same place, and it comes out different. The gravitational constant, unfortunately, one of the experimental results is it's not constant.
Well,
if you have a theory that says it exists
a function of temperature.
Then that must be wrong.
A function of temperature. So if you say
no, I'm not talking about different temperatures and stuff like that. I'm saying that you have various experiments that measure the value of G. So experimenter A measures the value of G. Experimenter B measures the value of B. They get 2 different incompatible results.
Depends on where they are. Yeah.
Not even where they are, even if they're in the same place.
G is higher over the oceans than over the land.
Within their experimental error, these two results cannot be the same. This is why the gravitational constant is only known to like 2 significant digits. Because we have so many experiments all pointing to different values that and we can't tell why is it one experiment shows one value versus another. For me, I think the key in that we agree that the gravitational effect isn't in fact an electrostatic, it's an electromagnetic effect. And therefore the type of experiment you build is like even like if you're building an experiment that measures the gravitational by having two masses is very typical in these experiments. Whether you have a vacuum between those two masses or whether you have air or any other type of material between those two masses, that's going to change. I mean, we just know it just electrostatically that the
Can I call a time out here for a second?
And that's going to affect the force of gravity. So,
Can I call a time out for a second?
sure, Alistair, you got something you want to say? Go ahead.
Yes. All right. So you've just given to Bill some challenges that you see he may need to accept the existence of those challenges you've suggested.
Yes.
All right.
You got some
Okay.
challenges. Yes.
All right. Now, don't assume what I'm going to say next. When people talk, myself included, sometimes what we identify as possible weaknesses in somebody else's explanation or claim are things we look for because we fear we may be having those weaknesses in our own claim. And so what I wonder is, Franklin, the challenges that you just gave to Bill, if you said, hold on a second, let me ask myself those same things. And then ask yourself the things that you just asked to Bill about your thoughts, your theory, your composition of reality. You were just mentioning to Bill about having to accommodate for what fills the space in between the atoms, which is what I had asked you. You've talked about predicting the masses of something that sits in the middle of something else. And I said, well, don't you have to be able to accommodate for that something else? Now you're telling Bill, don't you have to be able to accommodate for that something else? You're asking Bill the exact same thing I asked you.
Really? I don't think I asked that at all. I mean, I'm just kind of questioning Bill's stories about, the jet plane that can fly faster than the SR-71 and not blow up.
And then you started talking about the tiny things and then having to accommodate for what's in between. Is it air? Is it nothing? Is it something? That was what you were just saying to Bill when I called the timeout. But
no, not.
Okay, all right.
No,
All right.
were we talking about that? I don't think we were talking about what space is made of. We were talking about gravity and how do you measure? You're saying your theory can predict the gravitational constant, right? And I'm just saying that the one of the things you have to predict is that it's not constant. That depending on how you do your experiment, you should predict that you could get different values, and that if you have a theory which precisely predicts a value of G, then I would assert that you're missing something.
Let me call it timeout because that was one of my other things I noticed. So you're saying to Bill, you don't just have to be able to predict the gravitational constant. You also have to be able to predict that it's going to fluctuate and why it's going to fluctuate. Now ask yourself, Franklin, based on my theory of electron-positron pairs being the fundamental building block, how am I going to predict and explain not just gravity, but also fluctuations in gravity and why our measurements of them fluctuate? I'm just saying, you can, as an exercise.
Yeah, I was doing that. I was explaining that the reason why that is, or at least why I think that is in my hypothesis, is that gravity is strictly an electrostatic force. And we know that the electrostatic force is mediated through something that has permittivity, right? And that the value of that permittivity directly determines the strength of any electromagnetic field. likelihood of it. So I would say that you could do, my suggested experiment would be to take your gravity experiment and you change the material that between the masses, the test masses, which are in the experiment. So you do one which is in vacuum, and then you find the heaviest possible gas that you can stick in there, like argon gas. And you just, pressurize it as high as you can so that you change the permittivity as much as you possibly can. Now, if gravity doesn't have anything to do with the electrostatic force, then that should not have any effect. But I am predicting that you will get a different value for G in that setup than versus vacuum, right? So that is the experiment that I would propose to check this hypothesis that gravity is actually an electrostatic effect, right? By changing the permittivity value of whatever your whatever test masses you're using. So it could difference whether you are in gas mode, or maybe you could do the same experiment in water. I would predict, or you do the experiment with a steel plate between the masses, or lead plate between the or whatever. It's just anything to change the permittivity between your test masses. That would help prove that the constant G isn't really a constant. It depends heavily upon environmental conditions, right? And that there's other things I would predict is that perhaps the gravitational constant on the moon may measure different than the gravitational constant on the Earth. Now, it could be very close to the same. It would just be a matter of what is the ratio of the charge on each of these astronomical bodies. But theoretically, it could be different. So on the next trip we have to the moon, we should carry an accurate gravity G measurer and see whether it's the same as what we observe on Earth. I'm thinking that it's possible that we're going to get a significantly different number. Of course, then people ask, if that's not true, then why is it, things don't orbit and go crazy if G was like, see, now the deal with gravity is that the fact that things go in orbit doesn't actually rely on any particular formula or anything, because that's all we can observe is that we are in a stable orbit, right? Now, the force of gravity could in fact be, some screwball thing like 1/3 r cubed or something. And there could be other mitigating factors that make it so that we still orbit, but we can't tell that, or know that. All we know is that we are in orbit and that the orbit is stable, and we presume it's 1/r², and it makes sense that it's 1/r². Everything seems to work out that way, but in fact it might not be 1/r². It might be some complex orchestrated interaction of attracting and repelling forces that just happens to keep us in orbit, right? So,
One area that you may not have worked on yet is I've published papers showing since gravity is electromagnetic in origin, I've shown improved versions of the orbit equations and showed the quantization of the planetary orbits, which I don't think you worked on any of those areas. See, my background is I have a PhD in theoretical physics, and I was ranked as the highest PhD in theoretical physics the year I got it, and that got me the best postdoc position in the United States. But when you're in theoretical physics, you have all these different characteristics and experimental type results that you must predict, not just a few, but you've got the complete set. And so you're not considered successful unless you can do the complete set. And so that's what I have been working on. There are some areas that I'm still working, but so far I've had a great deal of success in producing these types of.
Yeah. So, good for you. But as the skeptic, I would always have to say that there's always a possibility that what you're doing is that you are matching the data. You're just you're just looking at the data, and whatever change you need to make to your theory to make it work, that's what you're doing. This is why in science, it's actually much more interesting if you can predict something that has not been observed. Like if your theory says that there is the soliton, and because it's this particular way, then we should actually be able to separate out the soliton particle from the electron. And I'll show you it's got the 1/3 charge. And when you do that experiment, then, that will convince people that that thing actually exists. But, until you do that, then all of this is building a castle in the sky, which is it all depends upon.
A thing can be known.
It hasn't been established.
Observation.
Yes, Alistair, I didn't quite hear what you said there.
A thing can be known to exist without direct observation.
It can, but it's better that it is. Like, for example, we've been able to directly observe the electron, and the positron. Clearly, those things exist.
Wait, maybe we should discuss the word observe. Are we talking visually, or
Yes,
are we
with your eyes? You can visually
observe, because our eyes are very limited, and we can observe experimentally using methods that go far beyond the ability of our eyes, and we know that. We know that we can go into infrared and ultraviolet.
Yeah, so we can use a microscope, and that's still using our eyes. That's fine.
Pardon?
We can use our microscopes, and we can still, use electron microscope. You can clearly see, the individual lenses of bugs' eyes, which we observe. But that's still observing with our eyes. I mean, I'm kind of like, seeing is believing, right? It's like you can't.
So we're talking
about making that stuff up.
We're talking about phenomena that are smaller, significantly smaller than the wavelength of visible light. So there is no visible observation of an object that is 1,000,000 times smaller than a packet of red light, or 1,000,000,000 or 1,000,000,000 or a quadrillion. You can't visually see that ever.
Yes,
period.
You can. Absolutely, you can observe those things. Yes, we can observe. No, we can directly observe an electron making a track in a cloud chamber. And you look at any science museum and you look at this thing, and it's amazing that in blank space we see all these trails, and those are individual electrons passing through space.
Wait,
and
did you see the electron, or did you see the trail? Because I said at the beginning, things can be known to exist without direct observation because you can see their silhouette or their impact. Then you said, no, that's not true. You got to be able to directly observe it. And then you said, we see electrons by their trail. Well, which is it? Are you seeing an electron?
Well, that is a direct observation. I would count being able to count their trail, which cannot be explained in any other way, as a direct observation. That's a direct observation, in my opinion.
You just did a bait and switch.
No, I would say that those kinds of things are a direct observation, because we're saying that there is a actual particle there. So if we observe directly its actual impact upon the environment, then that is a direct observation that thing was there, right?
Right. By impact on the environment, we can infer the existence of something we are not directly observing. True or not true? That's exactly what you just said.
I'd say that's a difference of opinion.
No, I'm telling you, we could rewind the recording, and you just said that based on the impact on the environment, we can know that we are directly observing, which we aren't. We're directly observing the impact on the environment,
which is a direct observation
of the impact on the environment. Like the direct observation allows you to know that the object casting the silhouette is there because you've directly observed the silhouette, but that is not direct observation of the object. So are you claiming that you can directly observe an electron, or are you claiming that you can directly observe the impact on the environment that the electron causes by passing? Because they are not one and the same. And I'm not saying that kills anything or supports anything, changes anything. I'm just saying at least be consistent.
Well, here I would say you're just getting your axle wrapped around definitional requirements. In which case, I would say that's a very unproductive activity.
Okay.
I mean, it's like all of science comes down to your opinion as to whether you're convinced that something exists, right? Now it's like, yeah, it's true. It's like if I see the electron in the cloud chamber, that's not an observation, and I can't, I haven't been shown the actual electron in like a picture,
right?
But
so
I'm convinced that there is something causing that, and if the scientists say that, okay, this thing is supposed to generate electrons, like I have a CRT or something, then they say this thing generates electrons. And when they turn it on, they put it in the cloud chamber, I see that making those tracks, right? And it does exactly what they say it is. Then, that's very convincing evidence that.
So did Bill mention 96 measured particles that need to be explained, that all have various masses and have all been observed?
Was there a question in there?
Yes. Either one of you can answer, because I'm sure I heard Bill say that there are 96 particles that have been measured. Measured means...
Yeah, I mean, you can make a beam out of them. Yeah, you can make a beam out of them, and you can play with them, and you can, know that you've got one versus the other, right?
Okay, so we've got these 96 observed objects now.
Yeah, like I said, is there a question in that? That's a fact.
Okay, sorry, maybe I misunderstood the various positions there.
I mean, that's total fact. The only question is, what are those 96 made out of?
And so then how do we conclude the electron to be fundamental?
Well, that's just experimentally. That they've tried every which way to break up an electron, and
sure.
I mean, they've broken up every particle. You can definitely
its impact on the environment, so we know that it's a something, but we don't know that it's fundamental.
Well, if it wasn't fundamental, then we could break it up into, say, somethings. Like if Bill's hypothesis is correct, the Bergman ring model, that it's made out of 3 sub 1/3 electron thingies, then it wouldn't be something fundamental. But no experiment that I know of, or at least nothing in the mainstream. Certainly Bill claims a lot of stuff that is not in the mainstream has probably been suppressed. But there's nothing in the mainstream that you would find that would suggest that anyone has done that. Perhaps.
That's not true. At the Space Radiation Effects Laboratory where I work, the people at the College of William and Mary did low energy scattering experiments of electrons off of electrons, and were able to show that there are 3 substructures in the electron by the way the scattering comes out. And we were the only accelerator center in the world at the time that could do those experiments. And we were reproducing what they had at CERN, but the ones at CERN did not work very well. And ours were able to do an experiment in an hour that took a year at CERN.
Yeah, well, once again, it's like you may be the only person who has access to these results, because obviously they've been, suppressed by the mainstream or whatnot. Me personally, that's important for me because, like the topic of the talk, and we're up to our 2 hours. So I'm going to kind of summarize here. So the topic of our discussion here was mostly about, how do dissidents react to controversial experiments that contradict their experiments. So, we started with draft physics, and we set an experiment that would contradict draft physics' hypothesis that everything is a packet, right, versus a wave. And then we discussed that I have a similar problem that I was challenged to show that only positrons and electrons exist, and that there can only be whole charges. And so we did the exercise of chasing down all of the references that were given to me, and we looked very carefully at those two papers to decide whether they had found something that critically disproves my theory, which is that there can never be any fractional charges ever, right? That's what my hypothesis says, because it's a quantized unit. It can only be generated. It is due to an actual wave that can only exist at one frequency. There can only be two frequencies. Therefore, there can never ever be fractional charges. So if anyone ever did come up with a fractional charge, that would say that everything I'm working on is just wrong, in which case I would gladly welcome that. It's like, okay, show me that. But in this particular experiment, they showed that there's a quasi-particle, and it's like, that's not a part, it's not an electron, not a real particle, some kind of geometric collection of charges that can apparently transmit less than a whole electron unit's worth of current or something. It's very complicated, but it didn't seem to get to the fundamental, my fundamental hypothesis, which is that for a actual particle, measurable particle, the only thing that can possibly come out of that is a whole electron charge. There's no other way for there to be anything other than that, is, say, my hypothesis. So that was kind of the topic for today. So thanks for everyone joining today. Sorry about all the technical difficulties we were having with StreamYard. Hopefully we'll try and, basically we're kind of locked out of StreamYard. We can't use it on any other computers. It's crazy. But hopefully we'll get those figured out, and hopefully I'll see you next week then. All right, thanks.
Bye.